Welcome back, everyone, to the Algebraic Graph Series seminar. Today we have Shaun Fallat from the University of Regina, who is going to be telling us about maximum nullities associated with a graph. I will let him take it away.
Okay, can you see everything there, guys?
Yep.
Okay. Okay, so just as mentioned in the introduction, I'm just going to talk about different versions of maximizing the nullity. Of course, these are nullities of matrices, but there are different ways to associate matrices to a graph. And it is interesting that depending on how you sort of set things up, sometimes these nullities do give rise to quite interesting phenomenon. So here is the sort of long outline of my talk. The first, certainly for about the first half, it'll be a little bit of history and survey of existing results and so forth. And then I'll move into some so-called strong properties, the last topic there, which is sort of a new trend, I suppose. Well, it's a variant of an older trend, but it's sort of got some new ideas in it, and I'll hopefully be able to sort of explain some things there for you. But just I just want to set things up for the purpose of my talk here. As mentioned in my abstract, the basic idea is you start with a graph, and I'll just consider simple graphs here, and I won't worry. I mean, there are other results related to non-simple graphs, but I'll just consider simple graphs. And then you associate to that graph a collection of matrices, and you can do so in many, many ways. A lot of us have done so. And then, once you have a list of matrices, you can start calculating your favorite property associated with a matrix. So I mentioned rank, nullity, spectrum, determinant, on and on and on. You can do those sorts of things. Now, for the most part, throughout my talk, this will be the base collection of matrices that I'll be worried about. So the matrices are real and they're symmetric. Okay, so that's the important thing. The size, of course, is governed by the number of vertices. And then the main restriction, I suppose, is that when you're looking off the main diagonal, the entries ij is non-zero if and only if I is adjacent to j. So off the main diagonal, you put non-zero entries in positions that are associated to edges, and you put zero entries in positions that are associated to non-edges. And then I don't care what non-zero number you put there, as long as you satisfy the symmetry condition. So whatever you put in ij, you must place in the ji position. And I don't restrict the diagonal in any way at the moment. So you're free to put whatever you want along the main diagonal, zeros, non-zeros, however you see fit. Once you sort of use this as your base collection, then there's lots of different ways to associate subcollections. And I make a comment here that an important one, okay, so that's important in my mind, is the subset of positive semi-definite matrices associated within this collection SG. And I mentioned here quickly the concept of orthogonal labelings of graphs, which is sort of a well-known topic, and I'll come back to that later. Now, for those of you that sort of studied the more typical matrices associated with graphs, adjacency, Laplacian, and then I mentioned its variants, so normalized, signless, all that kind of stuff. They all sit in this class SG, right? I mean, they're all described by the edges of a graph, and so they all sit in here. But of course, the set SG contains many, many more matrices. So here's just a simple example, just to waste some more time. So here's a graph. I don't have labels on the graph, but hopefully it's evident. I mean, labeling is not so important. I mean, and then, here from 1 to 2, I just put the non-zero number there because there's an edge, and there's no edges between the other two vertices, so you get zeros in that regard. So that's what I'm talking about. So you start with a graph, and you write down a collection of symmetric matrices like this. And then now you want to calculate, and for me, I want to calculate nullity throughout the rest of this talk. I'll just mention, discussing nullities of graphs is just a small part of a massive undertaking and problem that's many folks are looking at. And this is, I phrase it here as the inverse eigenvalue problem for a graph. And so the idea is, you just want to decide if a given multiset of n numbers is the spectrum of some matrix in S of G, where the size of the vertex set is n. Simple problem, but I mean, aside from some very basic graphs and small graphs, we don't really have complete answers here. So I just say some real simple things. A baby problem in matrix theory is that the only symmetric matrix with one eigenvalue is the scalar matrix. And of course, that translates into the only graph that realizes a single eigenvalue must be the graph with no edges, of course. And so that's the empty graph. And then if you think on the other end of the spectrum, namely the graph with all edges, it's not hard to work out this theorem, is that for the complete graph, so you start with a complete graph on n vertices, you can realize any set of n numbers as long as there's at least 2 elements in that set. And then all those can be realized. And those aren't hard problems, and they're easy, straightforward to work out. But in some regard, beyond this, it becomes very tricky to work out the complete answer to the inverse eigenvalue problem for families of graphs. I'll mention here the statement that I'm referring to. I call it Fiedler's tridiagonal matrix theorem. Excuse me. And basically, the idea was Fiedler wanted to know that what do the set of matrices A look like, so that upon diagonal perturbation, additive diagonal perturbation, you don't reduce the rank by very much. And so if you hold on in your hand a real symmetric matrix A, and you allowed additive diagonal perturbations in any way you wish, then and you want to preserve the rank being either n or n minus 1, then basically you're holding in your hand a tridiagonal matrix, an irreducible tridiagonal matrix. Of course, you can permute here, because of course that doesn't disturb rank. But for our purposes, basically, if you want the rank to stay high under arbitrary diagonal perturbation, additive diagonal perturbation, then you're basically holding in your hand a tridiagonal matrix. And so some sort of translations here is that a tridiagonal matrix, of course, the graph of a tridiagonal matrix, that corresponds to a path. And so if you replace the diagonal matrix D here by, say, lambda I, so now you're thinking about eigenvalue problems, this translates to basically saying the nullity, the dimension of an eigenspace cannot be more than 1. And so it must equal 1. And so this translates into the only graph that requires distinct spectra is the path, right? Every other graph, you can actually realize something with a multiple eigenvalue. And then you can work a little bit harder, and this was done long ago, that not only does the path require distinct spectra, but any collection of distinct numbers can be realized as the eigenvalues of an irreducible tridiagonal matrix. And so that's a resolution of the inverse eigenvalue problem for paths. Now, Leal Duarte worked a little bit in the late 80s and early 90s, and he basically showed that any collection of distinct spectra can be realized by a matrix associated with any tree, not just a path. This doesn't solve the inverse eigenvalue problem for a tree. It just says that if you start with distinct numbers, you can then find a matrix in S of a tree that has those eigenvalues. But it doesn't talk about the case of multiple eigenvalues. And then Monfred and Shader extended Duarte's work for trees to any connected graph. And then we worked a little harder to show that it's true for any graph. So for any graph, you can realize any set of n distinct numbers as the eigenvalues of some matrix in S of G, which I don't think is maybe not particularly surprising, but it turned out to be hard to actually work out. I'll mention in the context of multiple eigenvalues some results here, first due to Parter and then Wiener a little bit later. And this is in the context of a tree. And so it says, suppose T is a tree, and you take some matrix B in S of T, so some real symmetric matrix whose graph is the tree T. And suppose that symmetric matrix has a multiple eigenvalue. So the multiplicity of lambda, this is the notation for multiplicity, is at least 2. So I start with a matrix in S of T, and I happen to know that it contains a multiple eigenvalue. Then there must be a vertex in that tree, so that when you remove the vertex from the tree, so this is notation for removing the vth column and vth row from the matrix B, then the multiplicity of lambda has to go up by 1. And further, lambda has to be an eigenvalue of at least 3 components of what's left over. So let me just take a moment here. It is clear to probably everybody that if you start with a matrix, a symmetric matrix that has a multiple eigenvalue, then lambda will also be an eigenvalue of the principal submatrix when you remove vertex V, right? This is a result, for example, of interlacing. You can, you can prove this in many ways, but for example, it's a result of interlacing. So it's not at all a surprise that lambda reappears as an eigenvalue of the principal submatrix upon deleting row and column V. What is surprising is that its multiplicity has gone up. I mean, it was certainly allowed. There's nothing precluding it, of course, algebraically speaking, but it is a bit of a surprise. I mean, you would expect that as you delete rows and columns, the multiplicity of eigenvalues will sort of decrease. And it turns out that in the case of trees, there's always some special vertex where the multiplicity goes the other way. And that's surprising. But now let me just, take this tree here and let me just give you an application. Suppose imagine we hold in our hand a matrix B and the nullity of the matrix B happens to be 4. And it turns out that such a matrix exists. Okay, this is not fantasy. So then the question becomes, okay, so what can I learn from this? Well, in fact, using this Wiener theorem here, so I have an eigenvalue 0 with multiplicity 4, so it's multiple. So there must be a vertex for which, when I remove that vertex, the multiplicity of 0 goes up by 1. Well, it turns out that the 3 vertices here, the 3 vertices of degree 3, excluding the center, all have this property of the Wiener theorem, in fact. You just have to check. There's not a lot going on here. So if I remove these 3 vertices of degree 3, the multiplicity of the eigenvalue 0 has gone up from 4. It goes up to 5, 6, and then 7. And so what ends up happening is I have 1, 2, 3, 4, 5, 6, 7 vertices left. All, these are all independent. So it's just a diagonal matrix. And I have a 7 by 7 diagonal matrix, nullity 7, which means I have the 0 matrix. So if I start with a matrix B that has nullity 4, then it turns out that the diagonal entries of the pendant vertices and this guy in the middle must already be 0. So that's where you would use this theorem, right? When you're trying to sort of work with the inverse eigenvalue problem. If you start with something with nullity 4, then you've already forced a lot of things within this matrix. So I state that as sort of an example, hopefully an insightful example. Okay. So maximum nullity. So in its basic form, the way I'm describing it here is I take the collection S of G, right? So I start with a graph, I define the collection S of G, and I simply look at all the multiplicities over all the eigenvalues of A, and then I take the largest possible multiplicity, and then I do this over all matrices A in the collection S of G. And whatever number pops out, that's called capital M. Right? So it's the largest possible multiplicity of an eigenvalue associated with a matrix in S of G. Now, because I left the main diagonal free, I of course can translate any way I wish by scalars. So I in fact don't really need to talk about the multiplicity of any eigenvalue. I can always refer to the multiplicity of 0 because I can just move it to the 0th position. So capital M is also the largest possible nullity over the collection S of G, right? Because I can translate in any way. And so when we started studying maximum nullity, or when I started studying maximum nullity, I also became interested in the concept of minimum rank. So this is little MR right here. And it's exactly what you think of it. Is you just take the ranks of all the matrices in S of G and you take the smallest possible rank. Well, of course, a famous fact in basic linear algebra is that nullity plus rank equals the number of columns. And the same thing holds true when you maximize one end and you minimize the other end. You still get this basic relation. Some simple results. Duarte Johnson for trees showed that the maximum nullity of a tree is precisely the path cover number of that tree. So this is the fewest number of vertex disjoint paths that include all the vertices in the tree. And again, you can, if you think about the path cover number of a path, which of course is 1, you get back to the fact that the maximum possible nullity is 1, which is obviously related to the Fiedler tridiagonal theorem I mentioned earlier. The all ones matrix, for example, is a matrix whose graph is the complete graph. The rank of the all ones matrix is 1, and that turns out to be the smallest possible rank of a graph with at least one edge. But you can use that property to show that the maximum multiplicity of any graph is at least the number of vertices in the graph minus what's called the clique cover number. So the clique cover number is the fewest number of cliques needed to cover all the edges of the graph. And the cliques certainly don't have to be disjoint. But you can use this inequality to establish this last fact, which is kind of the other extreme from a path. And that is the only graph whose maximum nullity is n-1 is actually the complete graph, at least over the connected case. You can make up some examples in the disconnected case, which are just minor modifications of this. So the only graph with m equal to 1 is a path, and the only graph of interest with maximum nullity equal to n-1, the other extreme, is the complete graph. We started working on all, okay, what about the graphs with m equal to 2 or m equal to 3 or m equal to g-1 or g-1 is done, g-2. And if you look at the 4 graphs at the top of the page here, P4, K3, 3, and then these other 2, which have names, but I've forgotten them. I claim that you can check that the minimum rank of each of these graphs is 3. These 3 examples, it's not hard. K3, you have to work a little bit at, but it's not terrible. Why is this useful information? Because in fact, these are the only 4 forbidden subgraphs in this case. So if you want to characterize the graphs with capital M equal to g-2, you just need to check that the graph does not contain any one of these 4 as an induced subgraph. And that was done by others in 2004. And in some regard, that paper really spurred on a lot of interest in this problem. Let me move to orthogonal labelings of graphs. So this is an older idea. So what you do is to each vertex, you associate a vector as a label. And all I ask is that the 2 vectors be orthogonal whenever the 2 vertices are not adjacent. And this is called an orthogonal labeling. And then what you want to do is you want to try to choose the smallest dimension that you can kind of embed the labelings of those vertices and preserve this condition of orthogonality is associated to non-adjacent vertices. And this D here, if you minimize is that dimension, then you define that to be little d of g. And of course, little d of g is associated to some minimum rank of a class of matrices, in this case, positive semi-definite matrices associated with a graph G. It's not exactly the set S plus I talked about before, because you could have orthogonality in places where the vertices are adjacent. Whereas before I said you couldn't have that situation. But let me just finish this. And then of course you can relate the d of G to other graph parameters here that are associated. And there are folks in the audience that know much more about this than I, but I'm just pointing out that there is a way to associate nullity, if you will, flipping things around, to other basic graph parameters. Now, if you want to reassociate this concept of orthogonal labelings to the class S plus that I mentioned at the beginning, then there's another word you throw in, and this is this notion of faithful. So faithful in the literature just means that orthogonality if and only if the vertices are not adjacent. So this is more like the class S plus that I was mentioning before. And so what I'll do associated with this class S plus is I'll define the maximum nullity over all positive semi-definite matrices. And it was shown that this parameter M plus is at least the vertex connectivity. And was conjectured that M plus is actually at least delta, the minimum degree, but this has still not been formally proved as far as I know. And one other fact that I'll mention is that in fact, M plus. So the largest possible nullity over the positive semi-definite matrices S plus is equal to 1 if and only if the graph is a tree, it turns out. So all trees have the property that M plus is 1, and the only graphs that have the property M plus is 1 are in fact trees. And there is a nice application of Perron-Frobenius theory here, because Perron-Frobenius theory says if you have a entry-wise non-negative matrix, then the largest eigenvalue is simple. If you have an irreducible non-negative matrix, excuse me, it's simple. And it turns out that for trees, you can always re-sign this symmetric matrix so that all the entries are non-negative. And so or you can re-sign it so all the entries are negative. And so or at least non-positive. So you can use the Perron-Frobenius theory here. Now, more recently, we've decided to partition the set S of G by way of fixing the number of negative eigenvalues. So I just spent a little bit of time talking about S plus. Of course, S plus is you fix the number of negative eigenvalues to be 0. And so the question becomes, what if you fix the number of eigenvalues to be 1 or 2 or 3, or so on? So what can you learn from that? So here, as I said, S plus corresponds to S0. And what you could do is you can define the maximum nullity over each of these little slices. And so the nullity for each collection SQ is called, the maximum nullity is called MQ. And then of course, naturally, if you take the maximum over all the MQs, you return back the maximum nullity of that I defined originally. And so the question is, what is this going to get you? So here's a theorem that was proved by others. If you restrict the case to 1 negative eigenvalue, right, then for any tree, the maximum nullity over S1 is exactly the max degree minus 1. So there's another way to relate the nullity to a graph parameter. And then what we did recently with a former postdoc is we actually showed, I mean, don't worry too much about the wording here, but what we actually we were able to sort of construct is a Parter-Wiener type theorem in the case of S1. So if you happen to have a matrix in S1 whose nullity is maximal, and you're not talking about a path in the context of these trees, then you have these nice sort of properties, and they're reminiscent of the Parter-Wiener theory that was mentioned. And then what we were able to do is we were able to extend this beyond just 1 eigenvalue. So it was originally proved in this paper by BHL that in fact MQ, not just M1, can be calculated using just simply the graph. So it's this notation MDQ of T minus Q, where MDQ is referred to as the maximum disconnection number. So what this is it's the largest number of components that can be created from the tree upon the deletion of Q vertices. Okay, and so whatever that number is, that's called MDQ. And it turns out that the maximum nullity with Q fixed eigenvalues for trees at least can be calculated in this way. And we reproved it in our work, but it was known previous. And then it turns out there's a point at which you kind of plateau, and so that's called this Q0 number. It's just technicalities, but again, in the context of Q negative eigenvalues, we were able to come up with a Parter-Wiener type theorem in this regard over the context of a fixed number of eigenvalues. But in order for the theorem to be pretty, I suppose, is I guess the way to say it, we had to stick with this plateau number. You can say some other things for other Q, but it's not as convenient, and I won't bother you with on this talk with that. But this is just a Parter-Wiener type theory in this for the case of Q0 negative eigenvalues. And so I'll just make a comment that with regard to this tree, you can kind of track the maximum nullity. And as I mentioned, there's a place where it plateaus. So it starts at 1 because I told you for any tree, the maximum multiplicity is 1, and then it tracks up, plateaus, and then tracks back down like this. So you can use that work there to work that out. Okay, so that's just a very quick sort of rip through some ideas using the maximum nullity and how it relates to basic graph parameters and sort of what's out there. I want to switch gears a little bit to what I call strong properties of matrices. Okay, so here the idea is the following. So for a given graph and a matrix inside of S of G, I'm going to associate three sets. And these three sets, I give them the following names, or they're named accordingly. The first is called the isospectral manifold. The second is the pattern manifold, which is just another name for S. Excuse me. And the third is the constant rank manifold. And so you can view these things as indicated over the class of n by n symmetric matrices with the typical topology that you would associate there. So the isospectral manifold, these are just a collection of matrices B that have the same eigenvalues. So sigma here denotes the collection of eigenvalues. I apologize, I should have said that. And the constant rank manifold is just all the collection of matrices B that have the same rank as the fixed matrix A that you start out with. Okay, and what we're going to do is, of course, like many aspects of mathematics, you want to decide when two things intersect, or you want to solve equations, two things overlap. And what you want is you want the overlap to be nice. I'll leave it at that. You want the overlap to be nice or convenient, I suppose. And in this case, convenience will be transversal. And two things will intersect transversal. Here's the definition here. But according to the picture, it's something like this. Okay, so I mean, I'm not going to worry too much about all this stuff. It's not important for this talk that we get it down. But basically, something like this, we would not consider this intersection to be transversal because upon perturbation, things get ripped apart possibly, right? And so the implicit function theorem says that as long as things intersect nicely in this context, then perturbations will still intersect nicely, small perturbations, right? And so that's what this picture is trying to depict here, right? You start with the white picture and then you perturb and you end up with the gray picture, but things are still intersecting, not in the same spot, obviously, but you still have this intersection that you desire. Whereas if you perturb here, it's possible you will lose the property of intersection. Okay, so then what we have to figure out with regard to these manifolds that I mentioned before is what is a nice intersection, okay? And that's been, a lot of that work's been done. So what I'll do is I'll state things in terms of the normal spaces. And so for the pattern manifold, here is the normal space at a fixed point, at a fixed matrix A. So it's just a collection of real symmetric matrices, so that this is the entry-wise or Hadamard product. So A entry-wise product X is 0 and I entry-wise product X is 0. So this says basically that wherever A is non-zero, X had better be 0 in corresponding position. But X could have zeros in places where A also has zeros, of course. And here it's saying the main diagonal of X had better all be 0. The isospectral manifold, this is a basic problem in matrix theory. This is just a set of all matrices, symmetric matrices that commute with the matrix A. And in case of the rank manifold, it's the set of all symmetric matrices that satisfy this property, right? Columns of X are inside the null space of A. So, okay, so what we're going to do is we're going to go back and we're going to use this property of transversal intersection to work out, things that we want with regard to each of these manifolds. And the first thing I'll bring up is something that's referred to as the strong-Arnold property. So a matrix A, so this is a property about a matrix, satisfies the strong-Arnold property if and only if the only solution to these three equations, right, is the 0 solution. And what this means is precisely that the rank manifold and the pattern manifold will intersect transversally at A. That is, if the only solution to this list of equations here is X equal to 0, I have my desired transversal intersection for these two manifolds. And that was used in Coulomb-de-Verdier's work with regard to another subset of S of G. So it's a bit of a mouthful, but you can work it out. And basically the idea is that once you identified a matrix with fixed rank that had this strong Arnold property, then you were able to perturb things, so you could replace non-edges by edges, and you would preserve the rank. And so this gives you a way to move from the original graph to supergraphs, and then you could even go a little further beyond just supergraphs. And so here's the one of the results in Coulomb-de-Verdier's work. So let's just go through this together. Let mu be the maximum nullity over all generalized Laplacian matrices in S of G. So what I mean here is that these are matrices whose off-diagonal entries are required to be non-positive. Okay. I require exactly one negative eigenvalue, and that negative eigenvalue has to be simple. So the multiplicity is 1. And the matrix has the strong Arnold property. Okay, so this is a subset of S of G. It's a mouthful, right? But I just want to point out some of the results that was produced. This maximum nullity is at most 2 over this subset here, if and only if the graph is at a planar. And this maximum nullity is at most 3 if and only if the graph is planar. So this is I guess an algebraic characterization, if you will, of planarity. Now, what's really going on here, I suppose, if I can, speak to some of the experts here, is what basically happened, and I don't know if this is a happy coincidence or if it's just really, about looking at the right thing. Of course, planar, it's long been known that planar graphs are planar if and only if they don't contain two graphs as minors, right? K5 and K33. And it turns out that K5 and K33 have mu equal to 4, right? And so you sort of, if they don't contain K5 or K33, then mu has to be less than 4. And so it's not so much about checking planarity, if you will, but it's about using Kuratowski's theorem. And of course, outer planar are characterized, have minor, forbidden minor characterizations, and you just have to work it out. So I mean, it still isn't what I consider to be a fairly incredible result, but it's really about forbidden minors, right? And the minors are a result of consideration of the strong Arnold property. Going back to the path example that I mentioned before, if you take this graph here, the simple graph, and you write down the adjacency matrix, then the graph C here, it turns out it has the strong Arnold property. You check it, and here are the eigenvalues. Further, if you embed C as a block in the top 4x4 block, and then extend by the identity for any size, then this matrix also has the strong Arnold property. It can be checked. And so what is the actual consequence here is that if a graph has a vertex of degree at least 3, like there's the vertex of degree at least 3, then there will be a matrix B in S of G, so that the nullity of B is the same as the nullity of A up here, but the nullity of A happens to be 2. And so therefore the maximum possible nullity has to be at least 2. And so what happens is, if you have a vertex of degree at least 3, capital M is at least 2. So if you're interested in characterizing the graphs where capital M is 1, you just have to worry about graphs where there are no vertices of degree 3. And so there aren't so many graphs to check. And so you're down, well, here I just worried about the connected case for convenience. And so you're either worried about a cycle or a path, and you can check that easily enough. So this is another way to check that basically the Fiedler tridiagonalization theorem again. Going back to the set S plus, people restricted, or took a subset of S plus and said, look, let's consider the positive semi-definite matrices that also have this strong Arnold property. And this, of course, you have this inequality because you're restricting the maximum. It turns out that this parameter nu is also at least the vertex connectivity. there is work showing the connections between nu and, well, at least small values of nu and notions of planarity. And nu again is minor monotone, something like the parameter mu was previously. So it seems like when you sort of throw SAP in there, it seems like minor monotonicity sort of tags along, and that's very helpful. The fact that you have minor monotonicity actually turns out to be extremely useful. Capital M and capital M plus are not minor monotone parameters, and this is unfortunate. Going back to this parameter nu, in the case of chordal graphs, there's lots of work regarding nu, and so it was known previously that nu is between these two numbers, the clique size and the clique size -1, and of course nu, it was also known that it's never more than the tree width plus 1, and then we just worked out, myself and another colleague, when exactly for chordal graphs nu was this number or nu was that number. And the results are there. I'm just pointing this out as the sort of applications of these various nullities. Okay, so you have this parameter mu, which is it has the SAP, it's a generalized Laplacian, it has this restriction on the negative eigenvalue. Then it was sort of moved to the semi-definite case. So we asked ourselves, what if you drop semi-definite and you drop generalized Laplacian and all that stuff? What do you retain? So we came up with another parameter, z. We were running out of letters here, so we just chose z. So here it's just the good old set S, but you ask that the matrices A have the SAP, have the strong Arnold property. And so what do you get? Well, of course, because these other two parameters also had the SAP plus some other conditions, you obviously have this relation here. And then it turns out that these parameters are different, which is certainly not a surprise. But what was a surprise, I suppose, is that you still get minor monotonicity. So the minor monotonicity was not about semi-definite, and it was not about generalized Laplacian and that kind of stuff. It really, really was about the SAP, which I don't think is a huge surprise, but I mean, it had to be worked out. I point out that this parameter z does not really help in the case of trees. It mimics the outer planar property of mu that we saw before, but it did help in characterizing the graphs with capital M equal to 2. And I'm not going to go into that characterization. It was done by others, 2007. But the graphs that have capital M equal to 2, it turns out they're roughly speaking the same as the graphs that have z equal to 2. And so those are so-called basic linear 2 trees. But I won't go through it now. Okay, so moving on to the isospectral manifold, because I do want to just talk a little bit about connections to the inverse eigenvalue problem. So here, if you insist that the only solution to this list of equations, this is the commutator of A and X, is 0, then of course the isospectral manifold and the pattern manifold must intersect transversely. And you recover statements that are reminiscent of the Colin-Duvergier statement, but now with regard to the spectrum. So if you hold in your hand a matrix S of G and it has the strong spectral property, then every supergraph of G, not adding new vertices, just adding edges, has a realization B that has that same spectrum. And that's extremely useful, of course, for the inverse eigenvalue problem. Of course, you have to check this property SSP, which can be checked. I mean, it looks a little daunting, but it's not terrible to check. So you do get this realization for every supergraphs, and then you can work a little bit harder. So let me go back to remember I mentioned this work of Leal Duarte and Monfred Shader about realizing any set of distinct numbers. And here's a proof using the strong spectral property. So suppose you start out with a list of n distinct numbers, and you set those numbers in a diagonal matrix A. So remember, these are distinct eigenvalues along the main diagonal. The graph corresponding to A, of course, is the empty graph, because there are no edges off the main diagonal. There are no non-zeros off the main diagonal, so there are no edges. And the only symmetric matrix that sort of satisfies these three relations, the commutator and then these conditions, it turns out it has to satisfy these equations as you sort of go through all I and j. But because these guys are distinct, this will require the matrix X to be 0. And so this diagonal matrix has the sap. But remember, I'm starting with the diagonal matrix of just with those eigenvalues on the bottom. And it turns out that you can perturb that matrix to any supergraph on n vertices that realizes this same set of numbers, right? So this is, I mean, I don't know what the right word to say this, but this is like, you know, if I asked you to come up with a matrix whose eigenvalues were lambda 1 to lambda n, everybody would have just said, oh, the diagonal matrix with eigenvalue, you know, to put the diagonal in. Okay, of course. But if I asked you to do that, but, you know, have these entries non-zero, those entries non-zero, I mean, it's not clear that you should start with the diagonal being this and then do something else. And this is telling you how to do it. Of course, this is saying there exists a realization. I'm not necessarily showing you that realization, but nonetheless, it is the theorem. Going back to Colin Duvergier, as I mentioned, the parameter mu was minor monotone, which translates into a result like this. If you have a matrix A with the sap, and you have G with that's a graph minor of H, then there exists a B in the, you know, the larger graph for the nullity, so that it preserves the nullity. And the, you know, you can extend that idea to the strong spectral property. Now here, I have to be careful. So you fix a graph G, and suppose A is a matrix in S of G with the SSP. And if G is a minor of some other graph H, then it turns out there exists a realization in that larger graph whose spectrum coincides with the spectrum of A, so the eigenvalues coincide, but because you're adding more vertices possibly, you have to add more eigenvalues, right? And what you can do is you can add, well, what we were able to show is you can add a bunch of simple eigenvalues, you know, outside of the original set from the spectrum of A. So, you know, you have to be a little bit careful what you do here. But this theorem does help in some various aspects of the inverse eigenvalue problem. Okay, I'll finish up here. Just some notes. Obviously, I'm spending a lot of my time now worried about graphs with at least 2 multiple eigenvalues. I've talked about graphs with 1 multiple eigenvalue or 0 multiple eigenvalues. This turns out to be tricky. We have a characterization now of matrices of the graphs G that don't allow consecutive eigenvalues to be multiple, but we're still working on the more general problem. We know when the maximum multiplicity is, you know, 1, 2, or n minus 1 and n minus 2. What about these other cases? This seems, I'm not sure what the right word is here without sounding like I'm giving up, but this seems damn hard. The inverse eigenvalue problem, or, you know, that's hard. So people have come up with different versions. The inverse inertia problem seems to be one that a lot of folks are working on. So inertia of a matrix is just the number of positive, the number of negative, and the number of 0 eigenvalues. And so instead of specifying the complete multiset, you just specify that triple. And then I'm very interested in notions of zero forcing parameters that are connected to maximum nullity parameters. I didn't have time to talk about it today, but I think that's a really exciting area. At least I consider it exciting. All right, folks, I talked about a lot of projects today, and so it's hard for me to sort of classify which project belonged to which group, but I can tell you that I do appreciate the collaboration that I had. Former postdoc Mohammed Adem, a colleague Lon Mitchell, former postdoc Barioli, and colleague Hogben. And then I have, we've called ourselves the Focused Research Squares Group. We've worked in BERS and the American Institute of Math for a long time now. So this is Barrett, Butler, Hall, Hogben, Lin, Shader, and Young. Thank you, Sophia, for the invitation, and for Max, for example, for helping me out today. It is a privilege to speak in this seminar. I've enjoyed it so far. Thank you again for your time and attention. And here's some of the references that I tried to highlight in my talk. Thank you, folks.
Well, thank you for the talk. Wonderful. All right. So, do we have questions?
bunch
Yeah,
of questions. Some of them I think are a bit, I mean, I work on structural graph theory, and so some of them are more from that direction. So maybe I'll wait until later to ask about the Collin-Deverdier parameter and vortices. But one question is, so in regards to like say maximum rank and minimum rank, do these things work well over finite fields too? Like I'm wondering, especially if it's possible to do any minor monotonicity results over finite fields. But really, just if any of it works.
Yeah. So there's been work. Yeah, you switch the field from the reals to complex to finite fields. There's work on minimum rank. Maximum rank turns out to be not that interesting. I mean, in general, but I mean it's there, and I think you do realize different answers, right? So changing the ground field does change some of the answers to to these basic questions that I've asked. The Collin-Deverdier parameter. So this, I off the top of my head, I'm not sure, right? You'd have to work with these these manifolds over something other than R and C, which I'm just not an expert on, but maybe there's work to be done there. Yeah.
Thanks.
Yeah, of course.
Other questions? We can circle back to Rose in a minute, but yeah. I mean, the question I had was also sort of related to the minor monotonicity. I was wondering if you think there's, how strong you think the relationship is between minor monotonicity and strong Arnold property. Do you always think there's something strong Arnold-y going on when you have a minor monotone property, or the other way around? Like...
Yeah, I mean, it certainly does appear that strong Arnold gives you the minor monotonicity, and the question is, whether it goes the other way. I don't know. I suppose you could dream up a parameter that it probably turns out to be minor monotone that may not be connected to strong Arnold. I don't know, but any
chromatic number.
Sorry?
Like chromatic number.
Yeah, I don't know. I said algebraic parameter, but I mean, yeah, yeah. Okay, sure, yeah. But all I know is that whenever we associate a collection of matrices and you write down your favorite invariant, you very rarely had anything monotone unless you imposed further conditions. Yeah. Well, in my limited knowledge, yes. I mean, but it's a good question. Yeah, I guess all of those width parameters are all monotone, right? I mean,
I think so. Yeah.
Oh, so maybe you could do weird things like take monotone floors or something like that of these parameters, and maybe that'll give you, that'll turn things into being monotone, but they may not be that easy to calculate, I suppose. Yeah.
It's a curious connection, certainly.
Oh, it's very interesting. Yes. Yeah.
Okay. Other questions?
I'll ask another question if you've got the time. So I've been interested in also matroid theory, and there's a bunch of stuff about minimum rank completion problems where you get a matroid from it. So say you take, I think roughly you'd be asking the question of, you're making a matroid where the ground set is the edges of the complete graph. And you're asking, can every sufficiently generic matrix in this set that you're interested in, generalized adjacency matrices, can it be completed to a matrix of rank at most k? And that's like the k matroid, say, of your graph. And so it seems almost related to me. And I've been wondering for a long time, for years actually, although this isn't my main area, but if you can actually like get a matroid underlying some of these things, or if there's any connection at all, because I don't see a direct connection. Like you're allowing zeros to be changed to non-zero entries. You're not saying that for non-edges you have to put a zero. You're allowed to put other things.
That's right. Yeah, the short answer to your question is I'd have to think about it a lot more. I mean, other than at some point in a combinatorics class, I had to worry about matroids. I have not outside of that. So I have to, I'm sure there's a connection, Rose. I'm really sure, but I can't say it out loud in front of all these people and not look like a fool.
I definitely don't know the answer to this either.
No, I mean, there typically is, right? When you start worrying about things like rank, there typically is. I just don't know what this notion of completion and then what we're doing in this regard. I'm not sure the actual connection, but I'm sure there is, Rose. I just have to, if you point me to a paper or something, I'll have a look or an idea and I'll get back to you.
Yeah, I'd love to say that on the Matroid Union blog, just today, we had someone write a blog post about just what these matroids are and like the definition, because I guess the motivation somehow comes from algebraic geometry. And so it's hard to, I think, just read like a general paper about it, at least for me.
Sure.
But we had someone write a blog post that avoids a lot of that.
What field are you working over?
What
Finite
fields are we
or-
working over?
yeah.
C, in this case.
Okay, so
At least as the blog post is written.
No, very interesting. Thank you.
Thank you. I really enjoyed the talk.
Thanks.
Yeah, I think now is a good time for us all to thank Shaun again.